Namaskar. Welcome to Prakash on Basics. I'm Prakash Zog, and we have been talking on how numbers are, how big they are. Uh, how to write big numbers is what we talked of last time. It was typically what I told you as the standard form. So one digit, if required, followed by a decimal point and two more digits, and then a multiplier, which is 10 raised to x, where x is the number of zeros that you must add, or the number of 1 multiplied by so many zeros that must be multiplied to the original number. 3.00 into 10 raised to 8 meters per second is the velocity of light. That means 3 followed by 8 zeros, so many meters per second is the velocity of light, one of the universal constants that we know of. And I told you a number of different large values or very small values that can be written in a simplified manner. But once things get simplified, getting an idea as to how big they really are or how small they are is an error that many of us tend to make, because we really don't estimate as to really how big or how small numbers are. Uh, 3 into 10 is to 8 meters per second is what I told you is velocity of light, which something that I will come to later on is a light year, which is approximately 10 raised to 16 meters. That means 10 raised to 13 kilometers. 10 raised to 12 is trillion. So light year is around 10 trillion kilometers. On the other hand, mass of an electron is 9.1 into 10 raised to minus 31 kilograms. That means 0.00000, I go to 30 zeros and then write 9 and 1. And that's the mass in kilograms for an electron. Or the diameter of an atom is 10 raised to 5 minus 15 meters, or 10 raised to minus 10 angstroms. So these are numbers that are very big, very small, but these are very simple numbers that most of us can mathematically work on. Let's try and understand how really big these numbers are or how really small these numbers are. Let's choose the constant that I started off with, which is velocity of light, which is 3 into 10 raised to 8 meters per second. Uh, if I don't want to use meters, I can use kilometers, in which case three zeros will be reduced. That means 3 into 10 raised to 5 kilometers. That means in Indian languages, it is 3 lakh kilometers or 300,000 kilometers. Now, let's try and find out how this can be worked out in simplified manners when we talk of numbers that are familiar to us. I was just looking at the atlas some time back, and I worked out the distance between Moscow and New York, and this distance is 7,500 kilometers. That's the distance between Moscow and New York. Luckily, this number suits the other number that we have just talked of. So let's try and use this as reference. So if light has to go from Moscow to New York and back again, and if it does this 20 times back and forth or 40 times from one end to the other in 1 second, that is the distance that is covered by light in 1 second. 3 lakh kilometers or 300,000 divided by 7,500, which gives me a value of 40. So light will be able to go from Moscow to London 40 times in 1 second. The flight time that we know of today could be in the range of about 10 hours to 12 hours. So you can then imagine what is the speed of light. We can go one step further. I could talk of the diameter and then calculate the circumference of Earth itself. I'm not going into details, but this works out to be close to about 40,000 kilometers. So 40,000 kilometers is the distance traveled by a person when he moves around Earth once in a complete rotation. If I use light, then all that I have to do is 300,000 divided by this 40,000, and what I get is 7.5, which means light will be able to go around Earth 7.5 times in 1 second. So the numbers that we talk of, just velocity of light, is such a vast and a big number. But then things start getting bigger and bigger around. For example, this same light takes 500 seconds to come from sun to earth. So all that I have to do is to multiply this 300,000 by 500, and that gives me a value of 150 million kilometers as the distance from earth to the sun. Now, every time writing this is not going to be very easy. So, when they started measuring very large distances, they came up with another unit. It is known as uh, the astronomical unit of distance. This was the earlier one. AU, it is called. We know that the Earth really doesn't go around in circles, it goes slightly elliptical around the Sun. So there are two axes. The semi-major axis, it's a little different from radius. So it's a little more than radius. This is known as the semi-major axis. And this distance of the sun from Earth is taken as one unit. And that unit is called as astronomical unit. So mathematically, or in terms of numbers that we know of, it is 150 million kilometers is one unit. In one day, there are 60 into 60 into 24, that is 86400 seconds. Now, if I multiply 3 lakh by this number, what I would get is the distance traveled by light in one day. And so, when we start measuring distances up for much bigger values, uh, we come up with a new unit. It is known as the light year. It is the amount of distance traveled by light in 1 year. If I talk of the light hour, the value turns out to be close to about 1 billion kilometers. 1 billion. That means 1 followed by 10, 9 zeros. If I talk of a light year, the value works out to be close to 10 trillion kilometers. Number I told you some time back, 10 raised to 16 meters, which is 10 trillion. Trillion is 10 raised to 12. And my height is not even 2 meters. Imagine the actual distance that we are talking of in terms of a light year. So when you're talking of things like the solar system, you use a smaller unit. I can't talk of distance from Earth to Jupiter in terms of millimeters or centimeters or microns. So what do? I talk in terms of a standard unit. How far is the Earth from the sun? And how much further is Jupiter from the sun? This is what we can use common sense wise. So the distance of Jupiter is 52 astronomical units, which means 52 multiplied by 150 million kilometers. And the furthermost planet that we know of is Neptune, which is 30 astronomical units. Uh, Jupiter, of course, is 5.2 astronomical units, and Neptune is 30 astronomical units. And then once upon a time, we used to talk of Pluto. That Pluto is still further out, a 10 times AU more further. So it is at a distance of approximately 40 astronomical units. That means 40 multiplied by 300,000 kilometers. And that's the size of our solar system, because that's the position that we are talking of. But these are all ideas that were old. Now the ideas of what the solar system is different. I'm going to go into details of that much later. But let me just remind you, because we are talking of numbers, it will take roughly around 20,000 seconds or 5.5 hours for light to travel from the sun up to Pluto. And from there, we see a beautiful sun, something like this that you see behind. And from Pluto or from Neptune or from Uranus, it'll just be a bright star. That's all. That's what the sun will look like. And as I told you, the concept of what our solar system is increasing. There is a belt around of rocks and other material that is drifting around the solar system. It is known as the Kuiper belt, from where many of these asteroids and comets seem to turn up. That is between 30 to 50 astronomical units. But many of them come from a much bigger cloud that surrounds the whole solar system. It is known as the Oort cloud. Uh, I remember some comic based film in which special powers are given to people because of things, radiations from the Oort cloud and so forth. That Oort cloud is 2000 to 200,000 astronomical units away from the sun. Multiply that by 150 million kilometers, and that will be the actual value in terms of kilometers. And then you must be reading newspapers nowadays in which it is mentioned that the furthermost object, human made object, is the Voyager 1. How far is that? That's approximately 145 astronomical units from Earth. That means 145 multiplied by correspondingly 150 million kilometers. And it will take another 300 years to reach the Oort cloud. And 30,000 years more before it can come out of the Oort cloud and get out of the solar system finally. Far away. Light travels at 3 into 10 raised to 8 meters per second. So electrical signals travel at the same speed. Right now, Voyager's signal to reach Earth takes 21 hours one way. So when I send a signal back to it, it'll take another 21 hours more. So one way communication is going to be that far away. So you can imagine how big distances are. There are other bigger topics that are talked of, which is like heliopause and others. But let's talk of those when we come to the discussions related to solar systems. Let's bring the numbers closer to us and try and understand. Forget kilometers. Let's talk of Since I'm an Indian, let me talk of the population of India, which is at present estimated to be around 1.5 billion. That is 1 5, 1.5, followed by multiplied by 10 raised to 9. That means 1 5 followed by those many 9 zeros. Let's me go back to that Moscow New York distance once more. That was 7,500 kilometers, and luckily 1.5 is a related number. So if I one normal person, next one standing next to him, next one, next one, next one, not packed up. So let's say two people are fitted in a distance of about a meter and a half. Sorry, 1 meter. Let us say 1 meter. Our calculations will. That means 3.3, 3 feet 3 inches. That's good enough for two people to stand very close to each other. Now from Moscow to London to New York, suppose I make all the Indians stand one after the other and make a big line. There will be 100 lines from Moscow to New York. 100 lines horizontally, 100 people, 100, 100, 100, 100, 100, right up to New York at every in two people in 1 meter. I said, no, no, no. Why restrict to Indians? Let's talk of the of the world population, which is around 8 billion. Then there will be close to 533.33 lines. That means, let's say 533 for a change. So 533 lines of people repeated till they reach New York will be the population of the whole uh, Earth that we are talking of. Uh, these are this is only to give an idea as to how things are in terms of distances. We could talk in terms of time also, and time also. These big numbers, we don't really realize how big they are. uh, let me come back to the population of India, which is about 1.5 billion people. So let us say our beloved Prime Minister decides to shake hand with every Indian. Uh, Not every one of them, let's say half the Indian population. Even in that case, if he shakes hand with one person in 1 second, he will take 8,680 hours. That works out to be 361 days. That was nearly a year. 1 year just to shake hands with without non-stop. And if he just says hi and smiles, it'll take 2 seconds, in which case it'll take 2 years. That's how big the number of 1.5 billion is. There could be other things that are small and big that we could talk of. We know very small things. Let's talk of things that we know. We know. Let's say we talk of an ant. Then ants are of different size. How many ants are there? We see we hardly see ants around in the house. So sometimes you go outside or in the park and you start seeing a whole line of ants. There is a statistical estimate of the number of ants on Earth, and that value is 2 into rather 2 trillion, 2 into 10 raised to 4 trillion ants are there. That means 10 raised to 4 trillion is 10 raised to 12. That means that makes it 10 raised to 16, which means as compared to the population of Earth, the number of ants is 100,000 times more. So many ants are there. And how heavy is an ant? If you weigh an average ant, There are small and big ones, and average works out to be close to about 4 milligrams. Last time I was telling you about these suffixes centi and milli and micro and so forth. So this milli is 10 raised to minus 3. So it's 10 raised to minus 3 of a gram. But a gram itself is 1,000 times smaller than a kilogram. So it is 10 raised to minus 6 times smaller than a kilogram. That means there will be 1 million ants, rather 4 million ants. If I try and put the weight would one each one of them weighing 4 milligrams. If I take a million of them, the value will be only 4 kg. And then let's talk of a big animal. The one we can talk of a whale, blue whale, and so forth, but that you don't see. To estimate the size, let's say we talk of an elephant. So an average Asian elephant is around 4,000 kilograms. So 4,000 kilograms divided by this 4 milligrams. And if we calculate this value, it will turn out to be 1 billion. That means 1 billion ants weigh the same as just one elephant. You can just imagine. These are numbers that are there around us. We have seen an elephant, we have seen an ant. But what is the meaning of a billion? That's what it is. So, such big, large numbers also exist. But sometimes what happens is we tend to misinterpret, or we can't really judge some numbers. The instant you start talking of area and volume and things like that, it starts getting very difficult. Or rather, our estimates tend to go wrong. I'll just give you one example to clarify this. Uh, let's go back to the same numbers that I was talking of. So I'm talking of 1.5 uh, billion Indians. On an average, uh, a, a big, let's say, many of them. So I have one individual roughly around 1.7 meters in height. That makes it about 5.2 vagera, 5.2 feet, and around 50 centimeters broad. That means half a meter broad, and zero point 0.4 meters. That means about 40 centimeters, or a little more than 1 foot in his width. So if I length into breadth into height, if I multiply those, I get a value of 1.7 multiplied by zero point 0.4 multiplied by zero point 0.5. That works out to be close to about 1/3 of a meter. Now, if it is 1/3 of a meter cube, cube naturally. What is 1 meter cube? I take a length of 1 meter, a breadth of 1 meter, and a height of 1 meter, and that makes a cube. So, if an average man, an Indian, is 1/3 of a meter, it means in 1 cubic meter I can fit 3 Indians. I'm not even talking of them being adjusted, legs and head, because the width of the legs is far less than the width of the shoulders and so forth. I'm not even taking that in. I'm talking of a solid block and then working it out. Still, it is this. And I've not talked of small children. Well, half the population is small. I've not even talked of that. So, let us say that 1.5 billion Indians, their volume, if you put them in a box and stack them one on next to each other, this works out to be 5 into 10 raised to 8. That means 100 million cubic meters. Number seems to be big, but I am talking of a cube. And how do you get a cube? Length multiplied by breadth multiplied by height. And how much space do you think all these Indians will fit into if I put them in a cube? If you work it out, it turns out to be just 800 meters, practically three-fourth of a kilometer on each side. In about 10 minutes, you walk about a kilometer under good pace. So 800 meters is leisurely. If you walk for 10 minutes, that value is just a length of 800 meters. So you take 800 meters like this, 800 meters above and 800 meters this side and make a cube, and all Indian population will fit inside. It looks absurd because that's a pretty small size. And he says, no, why talk only of Indians? Why not talk of the whole world? So I was just working out, and that works out to be 1386 meter cube. The whole thing, each side being 1.386 meters. And even 1 mile is 1.6 kilometers. So if you take a cube of 1 mile length into breadth into height and put the whole world population inside, there is a lot of space left vacant. And how much water is there on earth? Surprising, the number matches. That is why I chose this number. It is again 1386 billion cubic miles. So much of water around and so few human beings around. Negligible, minuscule, microscopic. Those are the suffixes and prefixes that I was talking of long back. And does it work only for this? Not necessary. It works even for other things. Like, for example, let me talk of things like temperature for a change. We have studied all this in school, but in a different way. Uh, Ice is 0 degrees Celsius. Mathematically, uh, the next multiple will be 10 times more. So 10 degrees Celsius, that is fairly cold water. That is 10 raised to 1. And then if I take 10 times more, that is 10 raised to 2. That means 100 degrees Celsius. 100 degrees Celsius is where water begins to boil. I'm going from 1, 10, 100. So 1 degree Celsius is just molten ice. 10 degrees is fairly cold water. 100 degrees is boiling water. I take one digit more. I make it 10 raised to 3. 10 raised to 3 is 1000 degrees Celsius. And by the time I go to 1000 degrees Celsius, most of the metals that I know of have already molten down. Glass वगैरह is much lower. And if I go to 10,000, I have crossed that space where materials exist in the form of vapor, and I have gone into what is known as the plasma state. So the plasma is 10 raised to 4. I've just gone from 10 raised to 1 to 10 raised to 4. And all matter that I know of has broken down into either electrons and nuclei. And the temperature of the core of Earth is around 5400 degrees Celsius. And surprisingly, the temperature of the sun surface is also close to the same thing, which is around 5772 Kelvin. I remember when I was talking of light, I told you that the green color that we get is the peak value of the wavelength that comes from the sun. But that's the surface of the sun. What about the core of the sun? The core of the sun is 15 million degrees Celsius. See where we have gone. 1, 10, 100, 1000, 10,000, and 100 times more. How much hotter must it be? Think in terms of the ice to steam, and that's only 100 degrees. That is only power of 10 raised to 2. And going to all more metals and everything vaporized is another two more zeros. The core of the sun is two more zeros. A hydrogen bomb is two more zeros. That is 10 raised to 8 degrees Celsius is the temperature that is created when a hydrogen bomb explodes. And what is the hottest temperature that was worked out and calculated? It's at the instant the Big Bang took place, it is estimated that the temperature is in the range of 10 raised to 32. So difficult to even imagine how hot that really must be. And this is only in terms of numbers which are simplified and written. Think of the estimate of the values that they represent. Let me come to one more thing. Uh, our heart pumps 70 milliliters of blood around in one beat. So multiply it by that 86400 seconds in one day, and it works out to be 7,600 liters of blood is pumped around by us throughout our body in one day. It works out to be between 5 and 7 liters per minute is the amount of blood that our heart is pumping. And if I'm talking of a, a man like me, I'm 70. So, how many heartbeats have I finished? That works out to be some around 2.5 billion heartbeats. I was just talking of a cube, and I was talking of 1 meter cube. So, if I try and look at the amount of blood that can be calculated by a human being throughout his life, I'll have to start multiplying all these numbers together. And working out those numbers, I leave it to you to try and find out if you can really work out how much blood a person like me, say in 70 years, would have pumped around. Let me go at one more area. I was just referring to a meter. So if I take 1 meter, which is around this much, that's maybe about so much. That's about 1 meter, 3.3 feet. That's 1 meter. I break it down into 1,000 parts, and what I get is a millimeter. So, a scale of this sort, this is just a 12 inches, which is around 30 centimeters, standard scale. This is one third of a meter, and each line on it is 1 millimeter. Even this thickness of this blade is a little more than 1 millimeter. So, when I take 1 meter divided into 1,000 parts, I get a millimeter. If I divide that millimeter into 1,000 parts, each part is a micrometer. And if I divide that each part into 10 parts, then each part is the size of the wavelength of light that we are talking of. So the light you see around has a value of its wavelength that small. Meter, millimeter, thousand of these micrometer, 1/10 of that is 10 raised to minus 7, and 10 raised to minus 7 is the order of magnitude of wavelength of light. How small things are. Let me go to one more step. Let's talk of the nucleus and the atom. The atom is 1 angstrom in size. That is 10 raised to minus 10. How much is that? That means if I take that wavelength I talked of, divide it into 1000 parts, then each part is one atom. And the nucleus is dividing that atom size part into 100,000. That means 10 raised to minus 15 meters is the size of the nucleus inside. How small and how much is that? uh, 1 cubic centimeter. That means if you take that Rubik cube and take one chunk, one piece, that is 1 cubic centimeter. One cubic centimeter is along its one side. This you will be able to put 10 raised to 8. That means 100 million atoms. And if you make a cube out of it, 100 million into 100 million into 100 million, that makes it 10 raised to 8 into 8. 8 plus 8 into plus 8, that makes it 10 raised to 24. So there are 10 raised to 24 atoms in 1 cubic centimeter of material. How much is that? Population of the earth is 8 billion. Let's say by 2050 it will become close to, let's say, 10 billion. 10 billion. 10 billion makes it 10 raised to 10. So for every individual, if there was population as much as one earth, that will make it still 10 raised to 10 plus 10, that is 10 raised to 20. And 10,000 of such ones, if they are repeated, that will give you the number of atoms in 1 cubic centimeter. That's how big 1 cubic centimeter is when we talk of atoms. It is only trying to understand and estimate how big and how small these numbers are. Uh, and what about the nucleus and the atom that I talked of? Let's try and simplify things. Number wise, an atom is an angstrom, that is 10 raised to minus 10, or 1/10 of a nanometer. And the nucleus is a Fermi, that is 10 raised to minus 15. That means the difference between them is 10 raised to 5. That means uh, 100,000 is the order of difference between the nucleus and the atom. How do I estimate that? Let's say I take a marble of 1 centimeter size. That's about this size. I take that marble, 10 raised to 5 more from it. If I take 10 raised to 2 more, I will go to 1 meter, and another 10 raised to 3. That will make it 10 raised to 5 from the atom. That means 1 kilometer. So I take a marble at a distance of 1 kilometer from it. I put a very small ball bearing, that is an electron, and that is going around and round and round and round in all possible ways around this marble. And what I have is the simplest of atoms that we know of, with one proton in the center and one electron going around, and that's hydrogen. And if I go to the next element and the next element and the next element, the number of electrons in the orbits are going to change, but the size is good. Next one will be 4 times bigger. That means at 4 kilometers. Next one will be at 9 kilometers. Next one will be at 16 kilometers. Next one will be at 25 kilometers. And just 8 or 10 or 32 of those very minuscule ball bearings going around this 1 centimeter small nucleus that is there. And what is there in between? Absolutely nothing. So when Indian philosophy talks of the whole universe being mithya, not what we know of and what we feel, nothing is hard. Nothing is hard like this. All space inside is all that distances I've been talking of. So that's how small things are. And then light years and still more, and I'll come to parsecs and so forth. All these are very large distances. So understanding and estimating how big and how small things are. Our galaxy itself is 1,000 light years, and our universe is 10 raised to 13.7 billion years old. So these numbers, we should be able to understand and estimate them. That's the purpose of this. Uh, if you have liked whatever I have said, please like and subscribe to this channel. Look at so many things around you and try and find out how numbers are really, how big and how small they are. Make an estimate of things. Uh, Now that we know how big and how small things are, we can go into some more other areas that I really wanted you all to know as numbers and large and small things. The Big Bang and the universe and the solar system and radioactivity and other things. Till we meet for all of them, this is Prakash saying Namaskar. Bye bye.